of the sort of the workload that we are seeing today in the big data space. But first of all, what do we mean by big data? And there are way too many answers for that, but the reason it's becoming more and more common is because we are seeing a lot of sources where data is coming from. That's coming from traditional webs to mobile webs to wearable devices, from cloud computing to scientific computing. And the reason we are trying to even make sense of all these data sets because we can store them. Storage is getting cheaper every day. At the same time, and I don't have to tell you that our processors are not getting any faster, so to address the big data problem, we are building big data centers with thousands of machines and high capacity network to connect all these machines. And we are also building software systems that allow users to take advantage of all these resources in a scalable and fault tolerant manner. So it all started with, at least in the big data space, with Google publishing the MapReduce paper in 2004. And soon after, we saw Hadoop and Dryad in the open source world and also from Microsoft. And over the years, they were replaced by more complex engines, such as Hive for Hadoop and Dryad Link for Dryad. In 2010, in the AMP lab, we open sourced Apache Spark, which is now one of the most popular and most common sort of computing framework today in the big data space. And over the years, built on top of these frameworks, we have seen people building applications that work with graphs, that work with streaming data, that even try to do approximate analytics. And all these things are distributed. They run on many machines. And as a result, they have to involve the network a lot. And it turns out we have ended up with these big data stacks, whatever you call them, Hadoop stack, Spark stack, or something else. There are several layers. You have storage, and on top of that, you have resource negotiators that divide resources across many jobs that are running, that are sharing these clusters. And on top of that, you have execution frameworks, on top of which you have SQL applications or machine learning applications. And at the very top, there are users who have no idea what's going on inside. And because all these layers are distributed over many machines, they end up creating a lot of communication. And in this talk, I'm going to talk about what we have learned in the last few years about how application-aware networking helps and how network-aware applications can be sort of designed. So let's first start with application-aware networking. So first of all, what do I mean by applications in this case? Most of these are distributed data parallel applications and can be represented by sort of multi-stage data flow pipelines with interleaving computation and communication stages. So to take the simplest example, MapReduce, there are data that are all over the place in the cluster, distributed across many machines. And you have the map stage that computes, reads data, performs some computation. They try to read from local disk. So data and computer sort of residing or co-located in the same set of machines. And the next compute stage is the reduce stage, where each of the reducers reads some data over the network, shown in orange arrows here. They receive all this data, perform some computation, and same goes for the other reduce stage. And all these arrows together form the shuffle stage, which is the key communication stage of any MapReduce application. So after all these reducers are done, they will write their output to disk, and you are done with a simple MapReduce application. And one of the key observations here is that shuffle actually introduced a barrier. A communication stage like shuffle cannot finish until all the data has been transferred and they have been processed by the reduce stage. So, and this simple observation that there is a barrier sort of forms the basis of how we are going to do application-aware networking in big data analytics. And this is not limited to just simple MapReduce. Any arbitrary data flow pipeline, you will end up with several communication barriers throughout. And they have significant impact on the performance. To understand the impact of data transfers on this big data workload, we looked at sort of some production traces from Facebook clusters, where we found that on average, 25% of the runtime is spent in communication, and about 1/4 of the jobs spend more than 50% of the runtime in shuffle or transferring data over the network. And all these things are when they're reading and writing to disk. When you have more and more SSD-based and in-memory-based systems, the probability that network will be the bottleneck is only going to increase. So the next question we asked, what tools do these applications or frameworks have to address these networking challenges? And it turns out in traditional networking space, all communication happens in terms of a flow. A flow is just a sequence of bytes from a source and a destination. You have a fixed source and a fixed destination. some data is transferred, and this forms the basis of all allocation, sharing, and everything else that goes on inside a data center network. And over the years, in the last 4 decades, there have been tons of solutions that used flows to optimize, first of all, per flow fairness, meaning how do you fairly share the network links among multiple flows. And as data centers became popular, recently people are focusing on how to improve flow completion time. We don't care about fairness, we just want our flows to complete faster. How fast can we complete them? And as I will show in the next example, the flows are fundamentally inherently independent, and as a result, they cannot capture this collective communication behavior as we have seen in shuffle earlier. And to understand it better, let's take a concrete example where we have a shuffle. This shuffle have 3 senders or 3 mappers and 2 reducers or 2 receivers. Each of the sender is sending some amount of data to each of the receivers. And so, for example, sender 2 has 2 units of data for receiver R1 and 2 units for receiver R2. And we can model the entire data center network as a switch because there is more and more emergence of full bisection bandwidth network. We can actually imagine that inside there is not much of a sort of congestion, and the possibilities of contention only arise at the edges. So on the left side you have the senders, and on the right side you have the receivers. If we look at the shuffle on the network, we have this picture where the senders in this side of the input ports of this fabric is trying to send data over to the output side. And as I said earlier, there are 6 flows. And we are going to talk about what happens when we say use per flow fair sharing, which is provided by TCP or something like that, some protocol like that. And in this particular example, in the beginning, we are going to have 2 links that connects to R1 and R2 be the bottleneck because they are receiving 3 flows, whereas the senders are receiving only 2. And in the plot here, in the x-axis we have time, and in the y-axis we have bandwidth allocation of links to R1 and R2. So because of fair sharing, they will be divided equally between the 3 flows, and you will end up with these data transfers. For some reason, the graphic is not showing up well in this projector, but it looks fine here. But essentially, there are 3 flows going in on links to R1, and they got 1/3 of the resource share. Each block is 1 unit, so after 3 time units, they finished. And then the bottleneck shifts to the sender, and after 2 time units, this data is transferred. All in all, the entire data transfer, all the flows from this side that transferred these blocks of data to the other side, took 5 time units. That's when all the flows completed. And average flow completion time is 3.66, so like average over these 6 flows. And we have shown that there exists no flow-based algorithms that can optimize this any better because they are only trying to minimize or optimize flow level metrics. But we care about what happened to the entire shuffle, which I said is the barrier in this communication pattern in these applications. And one of the things we have shown here is if we know that this is a barrier, we can do much better. So if we use application level information, we can keep all the links busy at the same time. And what we can do, we can transfer all these data in 4 time units. So going back to the example again, we can actually slow down some of the flows that are finishing faster, take their bandwidth out, and give their bandwidth to the flows that are going slower. And we can make everyone finish within 4 time units using data proportional rate allocation. So we don't care about flow completion time. We don't care about fairness. We don't care about anything. We just care about when our shuffle finished. Our average flow completion time metric became worse. We are not fair. But at the end of the time, the users are seeing that their applications are running faster. So there is a fundamental gap between the applications and the infrastructure that have came into these stacks because of all these layers. And we want to strip this gap away. And to address that, we have proposed the Coflow abstraction that simply represents a collection of flows that have a common performance goal. And it captures the size of individual flows and where these flows start and end, the total number of flows. And these flows physically have no relationship with each other. You can look at a packet, it will not say how they are related, but at a higher level, from the user's point of view, they are related. They are part of the same communication stage. So using the Coflow abstraction, we can now represent any data flow pipeline as a sequence of computation stage and coflows. So in this case, we had shuffle, an aggregation, and a broadcast. And all-to-all communication pattern or a collection of parallel flows are also coflow. And a single flow that we have always used, point-to-point communication, is also a coflow with just one flow. Any traffic matrix is a coflow. And using coflow as the abstraction, we can now reformulate the problem as how do we optimize coflow level sort of performance metrics, such as minimizing coflow completion time or coflow level fairness, or meeting more coflow level deadlines, which are more aligned with our distributed data parallel applications bottom lines. And using this insight, we have built over the years several solutions that created coflow schedulers for different problems, and that provided a centralized architecture, and that provided an API for any application to easily use the coflow. And we have also, and I'm not going to talk about it, we have also discovered a completely new scheduling problem that we refer to as concurrent open shop scheduling with coupled resources. This is the first time we have observed this problem. Even we have talked to the operational research community, and this is the first time this problem has appeared anywhere. So what do these coflow-based architectures look like? Similar to distributed file systems or these application frameworks, Spark, HDFS, and whatnot, in this case, we are saying we will not allow anyone to communicate whenever they want. Communication will be managed by someone, and the users or the applications can only say they want data to be moved. It's not their problem how and when the data is moved. Someone else will decide and schedule what is the best for everyone in the cluster, depending on what is the parameter or the optimization metric that the cluster operator has set up. And in this case, you use a simple coflow API, and you just tell that I want this thing to happen, but actual timing and rate are determined by someone else. Similar to the way your data is managed by some storage cluster, your compute is managed by some scheduler. Only in networking, for some reason, we seem to believe that everyone should be allowed to talk. We need someone else to arbitrate when people should be talking and not talking. And we have seen that co-flow-based solutions perform significantly better than all other existing flow-based solutions that have been proposed in recent years. Proposals that try to do fair sharing, proposals that try to do minimize flow completion time. In this case, the lower is better, so Varis, one of the solutions, performs the best. And as I said, we assume that all the information about a coflow is known. So the difference between Varis and Allo is that in Allo, we sort of removed some of the assumptions that you can still do coflow scheduling without precisely knowing a priori what is the coflow size and where they start. And even if there are failures, we can very closely approximate a solution where everything is known. So it means that if we have this notion of what applications really care about, we can actually perform better networking in some sense. So the next thing I want to focus on, how can we do network-aware applications? So the first question we wanted to ask is, what do these networks look like in these big data clusters? Again, we went back to some production clusters, and in this case, again, we looked at this Facebook cluster, and we found that more than half the time, there is significant imbalance of network link loads in these clusters, and we observed the same for Bing clusters. So Microsoft Bing also has a massive data analytics structure where they perform many type of analytics jobs from variety of sources, and even their network is often imbalanced. Okay, so network is imbalanced. Next, the question is, where are this traffic coming from that are causing all this imbalance? It turns out a significant portion of this traffic actually comes from distributed file system. So first, we need to load data into this distributed file system. We need to read data from distributed file system. Whenever we perform some computation, we have to write our output to the distributed file system. So most of the traffic, a significant portion comes from shuffle, as I shown earlier, but the other more than half comes from this reading and writing and replicating and sort of surviving from failures of distributed file system. So what do distributed file systems look like? That's the next question. So in this case, I'm showing a simple example with 3 racks, and distributed file system forms the backbone of any big data cluster. In this case, files are divided into large blocks, and they are sort of copied across multiple machines to provide fault tolerance and partition tolerance. So each block is replicated across 2 racks and 3 different machines, and same goes for all other racks. And when we are trying to do all these replications, we are trying to make sure that the data storage usage is sort of uniform all over the cluster so that none of the machines become hotspots. And all this replication traffic creates sort of seconds-long flows, because as I said, the blocks are pretty large often, and you have to spend few seconds to move all this data around or replicate. And what we know from networking, as I mentioned earlier, sources and destinations are always fixed. You have a source, you have a destination, then you transfer data. The only thing you can play with is the path they are going to take when the data is moving around and the rate they are going at. It turns out these distributed file systems only cares about the data to be replicated into 2 different racks and 3 different machines. They don't actually say which rack and which machine. So this gives you the flexibility to figure out where they should be going. So right now what happens today is the network is completely isolated from the storage system, and storage system cannot talk to network to get a sense of what the network looks like. So what we simply did in this particular project is made this distributed file system network aware. It just asked the network that what does the sort of network load and imbalance look like, and it steers replication traffic away from the hotspots and into the cold zones and sort of tries to better balance traffic all over the cluster. And by doing that, we found that in both simulation and large-scale experiments on Amazon EC2, we saw a significant improvement in terms of job completion time and also in terms of write completion times, because we are always avoiding these hotspots. We are sort of making writes faster. And we also found that if our distributed file systems were not based on disks, but based on memory, something like Tachyon or Alluxio, which also came out of AmpLab, we can actually make things even better because we are sort of avoiding some of the disk bottlenecks. So over the years, what we have learned is that we can make things much better if we create this symbiosis between applications and the network, so that each one can use information about the other and co-optimize instead of trying to do sort of individual optimizations that often actually hurt each other instead of helping them. The next question is, what do we go from here? I mean, where do we go? And we have a single data center, and the more and more we are seeing that people are collecting data all over the world, and they are storing data to the closest data centers they can get to store data as fast as possible. So this is a map that I plotted sort of manually a week ago. And essentially in this plot, we are seeing sort of known data center locations of Amazon EC2 and Microsoft Azure and Google Compute. And as you can see, they are almost all over the world, except for Africa. There are like every continent has at least one data center location from at least one of these vendors. So even when you are not Google or not Facebook or not Microsoft or Amazon, you can actually have a global footprint. If you are doing some IoT stuff wherever your devices are sold, you can always collect data to the closest Amazon location or closest Azure location. It means that after you have collected all this data, which was fast because we went to the closest data center, now the problem you face is that when you try to make sense of all this data, you don't have any tools, because all the stacks that we have built in big data, they are for a single data center. They assume that all the data somehow magically appeared in the same place. So what people do today is they copy all the data from all over the world to some data center they have somewhere, and then they use the existing tools that we have, and they compute something, create some results, then they use CDN to distribute all these results again all over the world, and then they are served to the users. So what we set out to do in Michigan is we are trying to cut this middle stage. We don't want to bring in all the data, then compute and send it out again to the same place anyway. We want to compute wherever the data is as much as possible. So when we had these big data stacks before, it looks still the same as before, but instead of having them in the single data center as we have now, they are now distributed across multiple data centers all over the world. And these data centers are connected by a network substrate over the wide area network. They are sort of being used to transfer all this data around. So it means that we need to make our big data stacks aware of the fact that they are not really in the same data center anymore, and they are actually going over the entire internet. And in this case, network is king. The bandwidth is extremely low over wide area network, and it's very expensive. Cloud providers will allow you to store all the data you want for free, but whenever you want to take out 1 byte out of their cloud, they will charge you. So you have to make sure the amount of data transfer is minimized. At the same time, the latency over the wide area network is orders of magnitude higher than within a data center or supercomputer, and it varies a lot. You have to be able to sort of survive this high variability of latencies. And finally, the network over the wide area is not as reliable as that inside one data center. So it's very hard to predict what's going to happen, and we want to be able to sort of react to any changes that are happening online. And the project that we have started in Michigan, we call it Gaia, that's trying to create tighter symbiosis between applications and network in this geo-distributed analytics stack to provide better performance so that we can select faster path and react to changes in the path to minimize cost. And also we are looking into the privacy aspect of this analytics, because oftentimes you have data, you don't want it to be moved around. There are some countries like Brazil or continents like Europe, they want raw data to be stored wherever they are, not go outside the domain. So you want to provide access control on data movement and data access, but you still want to perform same type of analytics that you've been doing forever. You don't want to change the actual applications the users have written. So going back to the stack, we are trying to keep the entire upper level applications the same. So users and user-facing applications are using the exact same thing that they have been doing for the last 5-10 years. But we are trying to make the query optimizers aware of the network. When a query is being planned for machine learning or SQL or anything else, any scientific computing, whatever you want to do, they have to be aware that some part of it is in one data center, something else is actually many, many hundreds of milliseconds away somewhere else. And also, they have to be able to survive any sudden failures of paths and many other changes. In terms of execution frameworks, all of them are centralized, and it's very difficult to schedule sort of tasks over hundreds of millisecond latency. It takes several round trips just to know that a task has failed, and you need to restart it. Similarly, resource negotiators, when they were trying to fairly or some other way divide the resources, now they have to do it across many data centers over the world. So you need decentralized solutions. So we are again going back from a centralized world slowly back to a decentralized one, or at least a semi-centralized one. And the storage systems, when they are trying to provide fault tolerance of data center failure, instead of doing replication, they may be doing eraser coding that will save a lot of bandwidth. And they should also be aware of load balancing using this replication or eraser-coded traffic. And at the very bottom, where our core is, Gaia sits, is we have to do all the Coflow scheduling stuff that I mentioned earlier in a geo-aware fashion. We also have to design things that can survive path changes due to BGP vagaries or something else, and everything else that can go on inside the network. To give a quick example of how geo-distributed coflows will help, in this example, I have again 4 data centers. They are connected by some links, and there are 2 applications that are trying to transfer data. So the one in blue is transferring 5 gigabytes between 2 data centers, and the one in orange is transferring 10 from 2 different places to 2 different locations. So using TCP, what's going to happen is that these data transfers, given this topology, will take 10 seconds. Just trust me on this. These numbers, and for Coflow, I have calculated them. For Coflow-based solutions that we provided for the data center, where we assume that the network has infinite bandwidth in the core and only problems are at the edges, that will take 7.5 seconds. So you are aware of the applications, but you are not aware of the topology. You are assuming the topology is like a data center. So what we can do in geo-distributed analytics, we can actually use diverse paths, and a geo-distributed Coflow-based solutions that we are developing right now will give you the optimal sort of average Coflow completion time and average job completion time by doing joint routing and scheduling across wide area networks. So in summary, we have seen that there is significant opportunity to do performance improvements by doing application-aware networking and network-aware applications within a single data center. And we believe that all these things that we have learned over the years can be applied to this new and emerging scenario where, because of mobile devices and IoT devices, you will see this influx of lot of geo-distributed applications in near future. And all these things can be put together to perform better application network symbiosis in a geo-distributed world. And another thing that I can talk about offline is how we can perform application network symbiosis in rack scale computing, where instead of focusing on a single data center, we are focusing on a single rack that are very tightly connected with extremely high speed network, and how we can again exploit application level information to better use these high speeds networks. With that, I will conclude. Thank you.
Any questions for Mosharaf?
Thanks, Lou. When you were talking about the need to run with CoFlow in the beginning of your discussion, do you actually need to go through a learning phase to understand the different characteristics of the data being transferred and to be able to do that CoFlow optimization?
No, I mean, essentially, as a user, you just have to call the API, which is similar to BSD socket APIs. You have send, receive, open, close. CoFlow API is very similar. There is one additional call where you have to define that this will be a CoFlow. And so when you call the send, receive, you just have to give some CoFlow ID that will be provided by the framework. So users is only that and nothing else. So you can change your application to use CoFlows. And on the CoFlow optimization side, with the sort of latest solution, Allo, that I mentioned, that doesn't rely on a priori information about flow sizes and flow locations and failures and whatnot. In that case, we sort of learn as we go along what is the traffic metrics looks like for your particular CoFlow and how we can sort of leverage that information to still schedule CoFlows without having complete information.
Actually, I was going to ask Arno Kolster if any part of this is an issue that PayPal has been wrestling with.
The geo-distribution part is definitely something that we're looking at. I can't disclose much more at this point in time, but what I saw was pretty much in line with problems that we see in industry, as well as things that we've learned about in the past from the academic and scientific community, collaboration of documents and data. This is actually a perfect example of that work.
Well, I asked in particular because I know you're working with some folks in government on the problem, not asking you to give any details, but so what is being talked about here has, in your mind, relevance for lots of relevance for industry as well as
it's completely relevant
science.
for stuff we're working on, yes.
Okay.
And IoT is another perfect example of data collection at the edge, if you will, in distributed areas, and then pushing that data around where you need to push it.